In this lab, you'll be reacting vanillin, the major flavor component in vanilla extract. Vanillin will undergo an electrophilic aromatic substitution, where one of its aromatic hydrogens will be swapped for a bromine. Because there are 3 different types of aromatic protons on vanillin, you can get 3 possible isomers. And here are the 3 possible isomers: 2-bromovanillin, 5-bromovanillin, and 6-bromovanillin. Their melting points are different enough that we can use the melting point to figure out which isomer was formed in the reaction. There are many different ways to brominate an aromatic ring with electrophilic aromatic substitution. The conditions most commonly shown in textbooks use elemental bromine and some kind of Lewis acid, usually iron 3 bromide. These reactants are going to form Br+ in solution, or the bromonium ion. And this is the electrophile for the reaction. This is what attacks the aromatic ring. However, we are not going to use these conditions that you see in the textbook. The reason is bromine can be a little difficult to handle for undergraduates. It's a liquid with noxious fumes and quite toxic. Now, we will be using 48% HBr, which is no joke, but it should still be a little bit easier to handle than bromine. These are the reaction conditions that we will be using: potassium bromate, hydrobromic acid, and acetic acid. The electrophile in the reaction is going to be the same, bromonium, or Br+. The stoichiometry is a bit complex. Those 3 reactants are going to combine to form elemental bromine in situ. That bromine will react with acetic acid, so we're reacting it with a Bronsted-Lowry acid, as opposed to using a Lewis acid like is used in most textbooks. That is going to net us Br+, and Br+ is the electrophile. The electrophile will react with the aromatic ring to give us the brominated ring. In order to get the overall reaction here, we've got to play with some of the coefficients and then start crossing out things that appear on both sides of the reaction. So 3 bromines appear on both sides, 3 bromoniums appear on both sides. We also have, in the second reaction, 3 acetic acid. The acetate and the H+ produced in the final reaction are essentially 3 acetic acid molecules. Those go away. And then we have 3 hydrobromic acid molecules formed in the second step. And that will knock out 3 of the 5 that we started with, leaving us 2. Finally, we take what is left on either side of the reaction. We get 3 aromatic rings plus 1 potassium bromate plus acetic acid gives us 3 brominated rings plus 2 molecules of water plus potassium acetate. So here's that final stoichiometry one more time. You notice that the aromatic ring that you start with is in a 3:3 ratio with the brominated ring that you finish with. So essentially the aromatic ring is in a 1:1 ratio. We're not using benzene, we're using vanillin. So for every 1 vanillin molecule that we start with, we will get 1 vanillin molecule out. The reaction stoichiometry is very complex. However, the reaction setup is very simple. We'll just be doing this in an Erlenmeyer flask on a magnetic stir/hot plate. Make sure that the heat on the hot plate's off and the motor is the only thing on. In terms of safety, 48% HBr is very, very caustic. Glacial acetic acid will leave holes in your clothes. Both of them should be handled with care. Neither of them should be open if they are not being immediately used. And I would recommend that when you're carrying HBr to and from your bench. Please don't be carrying 5 other things at once. Use 2 hands. Please be careful.